Tonight, it's a real honor to introduce this year's Howard Lefevre Fellow, Brandon Clifford. This fellowship is a 9-month residency that provides the opportunity for an emerging practitioner to investigate a specific project and to develop their ideas through sustained research and teaching in the design studio. Tonight, you will see the culmination of Brandon's work in the form of this lecture, as well as an exhibition that will immediately follow that he completed in collaboration with Wes McGee. Within the spectrum of work that we've seen over the past decade or so that employs digital fabrication technologies, Brandon's work has moved from formal experimentation to claim a territory that is genuinely unique. If radical refers to a departure from the ingrained or accepted, Brandon's work is radically intelligent. So radical that some of it harkens back to a practice that we might have accepted as defunct, stereotomy. In fact, Wikipedia's primary entry associates stereotomy not with a medievally derived method of stone cutting, but to an album from the 1970s band, the Alan Parsons Project. So you know something is really dead when it's trumped by anything from the 70s. But that's what makes Brandon's work so interesting. On the one hand, it's pure structure, but while performance is necessary, it isn't sufficient. Within the work, the joy of making is made manifest, from the fabrication to the transportation, even via rider truck, to the assembly, to the final piece. Brandon received his Bachelor of Science in Architecture from Georgia Tech and a Master of Architecture from Princeton University. And from 2006 to 2009, he worked as project manager in the New York and Boston offices of Office Da. Following this, he served as editor of Pigeon magazine. In 2008, Brandon co-founded Matter Design with his exhibition collaborator, Wes McGee. This practice is committed to experimentation and research at a variety of scales and was selected as a finalist in the International West Cork Arts Design Competition. In 2011, Brandon was selected as a recipient of the prestigious Research and Travel Fellowship, the SOM Prize. And finally, I think one of the things that many of us appreciate about Brandon is that while his work is serious and rigorous, it comes from a person who's genuine, unaffected, and super witty. For all of these things, we thank you for what you've contributed to the KSA over this year.
Okay. Is audio okay? Ancient astronaut theorists believe that the architecture that's generated from these past civilizations, or maybe we can call them primitive civilizations, surely were aided by extraterrestrials. Because how else can you understand the fact that these civilizations that didn't speak to each other all arrived at the same form, that of the pyramid? So please keep in mind, ancient astronaut theorists are total wackos. Anyone that spent a little bit of time at the beach knows that when you aggregate things by stacking, they want to be pyramids. And this is something that eludes people that didn't emerge out of the French Enlightenment. They assume that primitive civilizations were savages and that we are enlightened. And yet there's a lot of lost knowledge in these primitive civilizations that we can retain. Let's not forget the lesson of concrete. The Romans knew how to use concrete, and then during the Middle Ages, we lost this knowledge. And only until the Industrial Revolution did we recover this knowledge that generated an entirely new form of architecture that we think of as the international style, perhaps. one of the best examples of an elusive architecture that these ancient astronaut theorists have projected are the walls of the Inca, and these are massive stones. So these theorists thought that the aliens had two machines with them. One of the machines was a liquefaction machine, because how else can you explain the sort of bubbly nature and character? And then they had a levitation machine, because these stones are way too big and heavy for humans to carry around. Keep in mind that these people claim that if we can't do this today, surely they couldn't have done it back then. So therefore, there has to be another explanation. And it's a bit of a religion almost. The reality is that the Inca had a few things. They had a lot of stone. They didn't have a lot of wood, and they had no steel. So this is like rock, paper, scissors. You can cut wood with steel. So we know they're not going to be working with wood. You can cut stone with steel, but they don't have steel. But you can cut stone with stone. So what's happening here is the Inca have developed over a long period of time, based on a very specific limited resource, the ability to use what they have. And they're carving stone with stone. So if you think about river rock, he's allowed to be here. That's Hakan. He put up with me for 2 months fabricating this thing, so he's allowed to be here. If you think about river rocks, that's basically what's happening, is that without steel, you can't carve precise edges, so you're going to round everything out. And the process they used was they would find a stone, and they'd make these little anchors that they could slip the wood that they weren't able to precisely carve into. And with a ton of men, they would carry this stone and place it above the location that it needs to go. So they have this seam right here. And they'd place it on spacers, and then they'd essentially scribe the bottom geometry onto the top stone, take it back off, hammer away with some stones until it got perfect, and then they'd place it back on, and you have this seamless joint that appears to be a bubbly character, and then they'd eventually pound out these custom hooks. So the point here is not that I don't believe in aliens, is that because that's a possibility, but I don't think that the Inca needed aliens. I think that they knew precisely what they were doing, and architecture does not emerge purely from an imagination of a single person. Architecture is generated based on a confluence of different issues and concerns: material, means and methods of making, tools, the imagination, and the ingenuity of a culture. So, Mark Jarzenbeck recently suggested that one could determine how well a society is doing by their ability to precisely carve stone. And this is pretty cool because you can track civilizations throughout time based on trade routes and see this sort of rise and fall of stereotomic knowledge. Stone is one of those things that you don't use after an economic crisis or a war. You use when you're going to build something of permanence that lasts forever, and you better know how to work with it. This matrix that Mark Jarzenbeck uses is really interesting also because it claims that we must not be doing so well today because we don't work with stone. And so much of the discussion around digital design has focused on the surface. And for me, this is the critical return to the topic of volume. Today, I'd like to present 6 projects that describe a research trajectory, and I really think that this year is situated right in the middle of this long-term project. We're just starting to understand how to work with volume and what it means. But let's begin, as long as there are no questions about aliens. No? I'll separate this just for credits. This is a project that I did at Georgia Tech under Nader Tehrani as professor. And then everything from here on, and this is in chronological order for the first time ever, is my collaboration with Wes, who's over here and will also be at the exhibition, with Matter Design. So let's begin, is this right? Let's begin with a softball. This is something that people would generally understand as digital fabrication. And it began based on the assumption that we'll learn how to make with sheet material. Because we're going to be donated $40,000 worth of polycarbonate from Baumer, and we also have a really badass 3-axis mill that flies through some acrylic. So to begin this project, you say, okay, well, we're going to make three-dimensional objects out of flat sheet material, and it's essentially an analog for paper. So one of the exercises that Naderi gave us was very simple. Just make a sphere out of paper. And here's an example. I'm going to fly through these projects, by the way. And this is the result, was understanding how to work with sheet material. We can accommodate a variety of different conditions. From the dumbest and most expensive bench in the world, this is just stacked up polycarbonate sheet, very heavy weight, that opens up and becomes a slightly more intelligent wall that expands and with a serpentine geometry to wrap around this column, and then breaking out into a space truss that spans across the distance to this beam, and then dealing with the condition of the cantilever. So how can, with one material, you transform a system to accommodate a variety of different concerns? This research was developed not only through drawing techniques, but also making and analog studies. So a lot of material understandings, detailed connections, finding ways of numerically coding the unit so we know which unit is which unit, and developing the details that will accommodate for the thickness of material. And here's the result. And I always like to say that this is the most interesting image for me because it's resolving three-dimensional objects into a detail that guarantees the people that put this together don't have to know anything about what they're making. They just have to follow the numbers. So this is a sheet material project, and this sheet material project is something that we're going to revolt against very soon, but a transition into this is the drawn dress project. Just a small caveat. At Georgia Tech, there are two types of students. There are industrial designers who get dirty and work down in the shop. Well, I can't say this is like really exactly what's happening now. Maybe it's changed. But in 2001 to 2005, industrial designers got dirty, they got busy, and architects stayed clean upstairs with their glasses and acted like they were better than making. Clearly, I'm making a position that architects can't just draw and make representation. They have to get dirty and understand how to make, because otherwise the Incas never would have generated their walls. Can you imagine saying like, I think I want a really bubbly wall out of some really expensive stone. Can you make that happen for me in Beijing for the Olympics? So the Drawn Dress project is my sort of inkling to be an industrial designer, even though I made the unfortunate mistake of becoming an architect in undergraduate. Wes was an industrial designer with a mechanical engineering degree. And this is the Drawn Dress project. So when I was working in New York, the building I worked in was full of fashion designers, and this is in the meatpacking district. I was really fascinated with the way they worked because not a single computer in the design houses. And if you go to an architect's office, there's guaranteed to be some computers today. Why is it that with all of this topic of surface and things like skin and bones or fashion and architecture, there are all these references to sartorial techniques like cutting, bending, folding, notching, pleating, so on and so forth. So what would it mean to use the techniques that we know as architects to generate a dress? This is the very first design, and I essentially mapped out the process that was used. Some very simple measurements were taken, a silhouette, the desired architectural intent, and then that unit needs to be discretized down into a series of developable surfaces, rendered to make sure that that's what we want, and then broken down into the 2D geometries that can then be cut out, sewn back together. And what we learned was that fabric and paper are not the same thing, and geometry and fabric are not the same thing either. So fabric really wants to do something very different. But we did learn a few things, and we felt confident enough that we could move forward. And And the next phase of the project was to go fully digital. We thought that this was the difference between architecture and fashion, was that we have computers and you don't. So let's get on Craigslist and we're gonna hire a model. And then in New York City, it's very easy, get her body scanned, which is much more precise than the measurements we took before. Although, well, I'll get to that. Remind me that she's a little bit fatter than she really is here. And the same process moves forward, and then you can test that design out and make sure that it fits. So what we learned after we placed this on the model is that the 3D body scanning people, and I can't name the company that we went to, but what they do is they intentionally inflate these things so that the dress or the suit that you make will fit, but just a little bit too much. So then you go back into the tailor and they'll slim it up. So there's no difference in the way that they're thinking. They're still giving you a stock thing that they then take back to the ancient techniques of going to the tailor. So once this process is done, these files are emailed over to Wes in Michigan, who's been busy building this fabric cutter to go on the end of the robot. Those parts are cut out and then stitched back together manually, keep in mind. We haven't figured that part out. These are the units that go together, and then here's the dress. There is some puckering and some things that are occurring in the dress that you can see as failures. It was a bit of a misunderstanding of what materials do, how geometries work, and I think what we really learned is that the reason why patterns are flat is that you want to sew in a straight line and you want to fold something up, whereas these seams and lines are drawn in three-dimensional space, and you're kind of like stitching things together like this through the sewing machine, and it's not very comfortable for the machine or for you. But what is interesting here is that once you figure this process out, you can make many dresses. And I think we made 5, and 3 were suitable to photograph. But if those two previous, If those two previous projects were really about surface, this is the revolt against the surface. And this was a competition for the 10-Up 10-Up competition in Atlanta for the Modern Atlanta event, which is a 1-week sort of design emporium exhibition thing that they have. And they made a call, and we responded with this entry. So the call was, we want an installation that will exhibit the future of digital fabrication and architecture. We're going to give you a 10-foot by 10-foot plot, $5,000, 24 hours to erect your design with 2 people. You have 1 month to fabricate it, and you get some equipment that we have. And the equipment is sort of like standard laser cutters, a 3-axis mill, and a 3D printer. But if you paid close attention, what they neglected to add into the regulations is a height restriction. And they essentially assumed that everyone was going to make 10-foot by 10-foot cubes. So our proposal was to make a signifier for this event and go as tall as possible. And this signifier sort of has a resonance in history, but we knew that the bigger you make something, the better it is, because Atlanta is a driving city, and you really want to see something from a distance to pull people in. So foam was the natural choice. It's a really great material. It's 100% recyclable, and there's 0 waste. But it's also extremely inexpensive, extremely light, and very volumetric. No longer are we working with sheets, which was really great. And we were able to make something very big on a very low budget. But about halfway through the project, our structural engineer sent me this image and said, Brandon, if you're going to build something really light and really big, this is going to be your problem. So this is the diagram that emerges. Basically, if you just stack blocks up, they're going to get blown over in the wind. So you really have to tie them down. And this functions in the same way that those punching bag inflatable clown things work, is that you can hit it and it can flex, but it will always stay vertical. And we thought this was interesting is that where generally with stereotomy, you're carving units to aggregate together, to stack on top of each other in order to resist gravity and make itself stand up. Whereas here, we're using cables to hold this thing down, okay? It's not trying to hold itself up, it's trying to hold it down. So there's an inversion in the process is that we thought in this competition we were going to be going up against a bunch of sort of tent installations, lots of fabric based on the price that they gave. So what we wanted to do was create something that appeared to be fabric. It had the rhetoric of fabric, something that's being stretched vertically when really it's being held down. And this is just for scale. It ended up being 50 feet, I think. Yeah, it's 50 feet tall. And these cables come up and attach to the top, and then they attach to the bottom. And this base was intended to be filled with water, that we couldn't get a hose that would fill it in enough time, so there were CMU blocks that were holding this thing down. It was constructed in sub-assemblies that could then easily be stacked up on site. Now remember, we had 24 hours and 2 people, so we had Tierson, who was a classmate of Wes's, and then Wes in the truck driving Tierson around. There we go. So we sort of followed that rule. And then eventually, the problem with this erection process, let me go here. The problem with this erection process is that while we were given 24 hours, in the summer in Atlanta, storms come through every afternoon. And until this thing is actually tied down, it's not working properly. So these things are just stacked on top of each other right now. And if a gust of wind comes, it'll blow it over. So we were lucky enough that right after we installed it and tied everything down, a hailstorm actually came and hit it, and we could see the tower flexing slightly. And this is the final image. So just a side note of this project, we went into a competition with the assumption that you're going to be building something like this with sheet material, and they're going to fabricate it for you. You're not going to fabricate it yourself. And the original site was back there in this corner, so hence the idea that we would make something tall because it's back there hidden. When they found out what we were actually going to do, and when the jurors awarded us the winning entry, they freaked out because they were afraid that this tower would blow over and hit this industrial concrete building. And I really love the irony of this because I hate the Industrial Revolution. It's given us so many things that have been detrimental to our profession. The contractor, for one, standardized, and I love contractors, don't get me wrong, I'll explain this. Standardized materials, like from here on out, what you will do is you will work with 2x4s. This is how wall assemblies go together. This is how you make a foundation, because we figured this out and you'll just keep doing this. You don't need to invent anything. This is precisely because we've separated the means and methods of making from the process of architecture. So the architect is relegated to just making representations. So the way we work today is we make drawings, we put notes on the drawings. The drawings don't have to be correct as long as the notes are correct. We send that off to a contractor. Keep in mind this competition. We send it to a contractor who will make it. And they have specific materials and processes that they use, so they will in turn tell you if what you've drawn is capable of being made. And there's a sort of reciprocity that occurs there. But if you actually start engaging in the liabilities of construction, you can invent new methods of making. So here's a project that sort of is the second iteration of this foam carving. And it was a thesis that essentially stated that our profession has also been dedicated to this idea of permanence, and we'll never get out of these foreclosure problems in cities like Detroit if we continue to work off the principle of a 30-year mortgage. So just as a baseline assumption, we're going to do away with a 30-year mortgage and see if we can develop an architecture that's based on a 6-month mortgage. So you can no longer get shingles that have 30-year warranties. You can no longer work with windows that have 100-year warranties. You can no longer work with siding that has 30-year paint warranties. So everything in the industrial catalog of materials that the contractor works with is based on this assumption of 30 years. So if we undermine that, we need to look for material and a process. So the architect can no longer be super slow, they've got to speed up. Okay, so we skipped this in the tower, but here is, sort of a demonstration of the idea of carving with wire. This is a really great process, and we'll get back to this idea of cutting with a line instead of a point. But if typically you're milling based on a point, moving back and forth, or laser cutting based on a point, you're always going to have a problem with time. Things take forever. Whereas this process uses the developed surface rule that actually follows the geometry based on the line. So this line is much more efficient at carving blocks than a point. So the idea is, of course, that you have a constantly recyclable material, that after the 6 months, this material has probably degraded a little bit. You'll regrind it, extrude out a new block, and make a new architecture that isn't just able to accommodate the foreclosure rates, but also brings up questions about what does it mean to do architecture that only lasts for 6 months? What are we going to start responding to? Will things be as general and generic as they were previously, or can we get more specific and create architecture that's based on seasons, for instance? So the idea is that after these units are carved together, they'll be post-tensioned to infrastructure, a very rapid method of erection. And this was tested in the gallery space the night before the review. So what you may not be seeing is there are some little holes in here, and there's some string that's being strung through these things. And Joe and Jane are down here. They're about to tie off the strings to the bottom, or the foundation, or the infrastructure. And then I'm up there, and I'm about to start ratcheting that cable to hold this thing taut. Now, we only had some ratchets. If we had a winch, one would hope that this whole thing would kind of erect itself, be much faster. This was much slower than I would have hoped. But what is interesting is that this whole thing, including shipping from Ann Arbor to Princeton, New Jersey, was less expensive than the MDF base that my team was able to make in the 2 weeks that I was gone. And it's not because they didn't know what they were doing, it's that they were working with standard processes, and sort of the industrial era has them by their balls. So here's the project, and the cable, you can see the cable running through, but what's important here are the ruling lines that geometry is following as it skips over the corner, loops back, and traces itself again. Okay. So I've just shown you 2 sheet projects, or 2 paper projects, if you will, 2 foam projects, and now we'll get into wood. So this year was dedicated to finding a heavy material, because the irony is that I have this interest in permanence, things that last forever, and yet I keep doing these temporary installations. So again, we're industrial designers of a sense, and this coat rack was a translation of a typical coat rack, this sort of 3-stick typology, translated into the digital era. And here we have 3 of the same unit that can easily be shipped, and then they're bolted together. And the way that this is made is essentially one half of this is carved out on the 5-axis mill, and then flipped over onto the custom jig that vacuum holds this thing in place so that you can get it from the other side. The problem of carving a solid 3-dimensional round object out of stock material is not easy, actually. And this is sort of the first inkling that we had moving towards this project over here. So you can see that these units are then bolted together. Here's a detail. So they're pre-drilled at the specific angle so that the little belly buttons can receive the bolts and cinch this whole thing together. And this is Hakan. He's in the back. Okay. La voûte de Lefebvre. So here's the project. And I'd like to not show final images of the project because hopefully we're all going to go and experience the project right after this. So everything should be cropped slightly. Am I doing on time? Okay. And the only way to describe this project is to describe the process of computation that was developed. So thick funicular is a project or a computational model or program or whatever you want to call it that emerged from a question that if you think about form finding or the catenary shape or the hanging chain model, you'll always get an ideal geometry that assumes uniform thickness through time, and yet somehow the Gothic masons were able to make something stand as a compression-only structure without following that ideal geometry. And they were able to do that through thickness of material, weight, volume. So this spire, the weight of that spire is actually redirecting the thrust vector down into this thick column, because otherwise that shape would go out here and everything would fall down. So if you take that spire off, this thing falls down. It's not just ornament. So here's the idea. If this is form finding and we assume ideal thickness, this is an engineer's approach. It has nothing to do with form. It says that form is based on gravity, and we will work with the form that's given to us. Whereas the claim that I was making was, what if we give the model the form? So here we've removed the column. This is an ideal form for architecture that deals with things like acoustics, structure, space, function, you name it. Architecture has to accommodate all these things, and structures only accommodate one thing, loads. So we needed to find a model that would compute the distances and the thickness to make sure that we could create something that would stand up. And here it is. We'll see a live version of it in a second. But essentially what's happening in this model is you get a hanging chain that finds a vertical intersection with this bottom architectural geometry, and it informs that particle with a new weight. So this particle weighs more than that particle, and that's why you're getting this kind of like wonky shape as it goes over. So as long as you compute this in this way, you'll be able to generate something. I think I just screwed up. Here we go. You'll be able, so here's the model running. And what it does is it produces an absolute result that says you were guaranteed a compression-only system when you put these things together. So right now the model is expanding and it's going over, and it expanded too far, so it's going to shrink back, and there's sort of a bouncing that occurs here. But you can see what it's doing is it's finding this variable thickness to make sure that we can get a compression-only structure. Now, this geometry is totally arbitrary right now. It's just an odd shape that we can use to test this model and make sure that things are working. But what you'll notice is that if you move that geometry through this arch, the arch will respond and give you a new variable thickness. Okay. And then once you do that and you have your final geometry, you can prototype this and make sure that, yes, this thing actually needs that weight to stand. Here's the spire again. So all I did here was tell the particles that are in here that they weigh 8 times more than their neighbors do. Now, this is very legible in 2D, but the model has expanded. Once you can do 2D, you can very easily do 2.5D, which is just an array of these things over and over again across the surface. The 3D mesh is a bit slower, but it's exactly the same computation, and it's pretty unwieldy, actually, because in these things, at least you can control the locations of individual things, but in this system, if you move one thing, it moves everything. So you really have to balance things out. And then a composite system, this is a projection of maybe using something like a ribbed vault, where you would thicken up the ribs and then you would use the ideal geometries to span between, sort of the Catalan approach. And of course, these were also prototyped. But it's pretty crazy because those are really, really thick sections, and they weigh a lot, and it would be very expensive to make them. And while I would love to make something that's very thick and heavy in the gallery, it was actually really impractical. So we needed to regroup and find the second iteration of this computation. So this is the volumetric funicular. And the way the volumetric funicular works is we start with what is a non-ideal stretch geometry. So if we follow, there is missing in this drawing, there is a surface that's describing these things that have been stretched vertically. And then there's also an offset of that surface, which is variable thickness. So for instance, around the edges, I think it's 2 inches, and then it changes thicknesses up to 8 inches, 12 inches in different areas. The model does not know or tell you where this variable thickness occurs. That was something that I gave it. And then these particles have springs, and the way this thing works is that the particles all start down here at the bottom, and the further up they get, the further apart they want to be from their neighbors. So they sort of stretch out and they make their way and they expand across the surface. And then those particles respond by creating cells, and each cell determines its volume. Whereas before we were calculating vertical distance, now we're calculating volume of units. So each one of those units can respond to its volume and say, I'm actually heavier than I need to be. I need to be much lighter. So what it will do is it will open up a circle and sort of remove material from the volume. And if you blur your eyes, you can see these units. So the geometry that was generated here was a conical Boolean. And each one, so let me see if I can trace a cell. So this here is a cell, right? So this cell, well, let's go here. This cell doesn't weigh a lot. This cell weighs much more. Now, the result that comes out of this guarantees you that what you're going to build is a compression-only structure that will last forever through eternity, right? It has no tension, and the only way it will fall is if you take a crane to it. And the problem here, well, let's back up. So we can compute things and we can make things at scale all day long, but you're going to enter into a completely different territory when you start making it full scale. And I think a lot of the sophomores that are in here are probably engaged in this same problem. So you have to get dirty. And I'll see if I can map out the process of getting dirty here. But this behind us, behind Aaron, is the 5-axis mill. And what it's doing right now is it's cutting out just template cuts, profile cuts, that are then intelligently sort of stacked together to rough out the geometry of the unit that needs to occur. So instead of just getting thick stock material to work with and carving away all of that excess, we sort of rough it out first. And then those units are placed in the vacuum former, held down for 2 hours. When that's done, they're lifted up and placed on the 5-axis mill so that everything's re-indexed again. And here's the process of cutting. So pay close attention. This is the stock rough that we're given. And then the bit here, here's the roughing bit. So we've roughed out and gotten rid of a lot of the material. Then there's a finish pass that occurs. Then there's what's called swarf cutting. And the swarf cutting, in order to create these units that will bend over the top of us, the edges of these units can't be vertical. They're actually tilting and changing through time. So the bit, and we'll see the video, the bit sort of moves around like this in space. And that's why, I think we've got an image of that. Why don't I explain? Understand that the same principle of the line that we were working with in the foam is the principle we're working with here. So we're carving with the edge of the bit, not the tip. So it's much, much faster and efficient. The holes are drilled to index them, the parts are cut out, and here you can see the swarf cutting, so there's a slight angle that's occurring here that might be more obvious in the video. But here are the bits, here are our tools that we're working with. And a very sort of uniform project emerges out of all of these different bits. And just for comparison, this is kind of a standard prototyping router bit that you might see regularly, and this is what we're working with to swarf cut. So when you bump up in scale, there's going to be a limit where you can't keep using bits. I mean, it takes forever to cut something out. Those parts are then shipped back down here in the back of a truck, which is its own sort of design exercise to get things in. And also the size of the units are determined based on our assumptions about how much weight someone is willing to hold over their head while they're installing this thing like Michelangelo. The units are arrayed out in the main space so that we can find the parts and make sure that we have all the parts we need. Each part is labeled with the location, which is right here, and the part number, the unit number. Because, again, they're all unique. So if you're missing a part, you're screwed. Some trig and a plumb help you create an RCP drawing on the floor that can then determine where the rest of the units need to go. Not the units, but the frame. So this is sort of interesting, the back edge. While the front edge is seamless, hopefully, the back edge sort of follows its own path and trajectory in order to make this thing work. So here's how the installation process begins. These units are hung from these beams, and they're only hung for the installation process. After the process is done, the columns are holding them up, and it's self-supporting. So there's a compression ring that wraps around the whole thing. And I think this is the lesson. I mean, every time we make a project, at the end of it we say, oh, why didn't we just do it this way? And it's like the most frustrating thing in the world, but there's still a lot of this that happens when you're working with volumetric materials. And it's great to work with wood because you can just cut it, you know? If it's not right, just cut it. Okay, so in the end, let me just play the video while I'm concluding here. In the end, it turns out it's really difficult and a lot of work to make a heavy architecture out of volumetric materials. And I think that the only way that we can progress is to keep on pushing ourselves further, trying to do things that may be difficult, but are uncharted territories for our time, by the way. I'm talking about our time. These things have been done before, clearly, but we've lost all that knowledge. And I think that the next path for us is to actually engage in a program, an architectural program, although these previous projects have been installations, dealing with things like infrastructure, other materials like aerated concrete, solid stone would be great, or finding ways of making that aren't dedicated to the standardization. And you can only do this through reciprocity between drawing and making. And I hope that's what's emerged out of this process, is that I want us to start making again. Thank you very much.